This is Mr. Martin. This video is covering section 7.4 for Honors Pre-Calculus. We're going to be talking about matrices and systems of equations. So a lot of this you probably already know how to do. You know, some of it is going to be new, but most of it will be stuff that we've kind of talked about informally. So we'll do it a little bit more formally now. So let's talk about the definition of a matrix. So if m and n are positive integers, and m by n matrix is a rectangular array. So you see we start up here in the corner with entry A sub 1, 1. So the first one is for the row, and the second one is the column. So this is the first row, first column entry, and this would be the nth row, nth column entry. So we always read it as rows. So rows are going side to side by columns. Let's get that n in there. Okay, and columns are up and down. I'm not sure why we call the rows in school rows, because they're really columns. But so then if we're talking about the order of a matrix, so this first one has one entry. So this is a 1 by 1 matrix. Its order is 1 by 1. So for part B, we've got 2 rows and 3 columns, so its order would be 2 by 3. And then the last one, it has 3 rows and 3 columns, so it would be a 3 by 3. So anytime you're asked for the order of the matrix, really we want to know rows by columns. All right, the second example, again, a little bit of vocabulary. We're talking about an augmented matrix. So given the following system, write the augmented matrix. So our augmented matrix is basically what we do when we pull off the coefficients. So my coefficient of x here is 1, my coefficient of y here is 1, my coefficient here is 1, and then it's going to equal 2, and then we'll go ahead with the other 2 rows. We have 2, negative 1, there's no z term here, so we'll put in a 0, and 4, and then in our third equation there's no x, so we'll put a 0, and a 2, and a negative 1, and it equals negative 2. And we've been working with these already, particularly when we were doing partial fraction decomposition. We could go ahead and solve this if we wanted to. We would probably use reduced row echelon form, which we'll talk about a little bit more in this video. Actually, we're going to talk about it right now. So example 3, it says Gaussian elimination with back substitution. So really what we're going to do is solve using reduced row echelon form. All right, and we're actually going to do this example first, which you should hopefully know how to do. If you need a reminder, this hopefully will remind you how to do it. So we're going to write our augmented matrix. So we have reduced row echelon form for 1, 3, 4, 7, and then 2, 7, 5, 10 for the next row. 3, 10, 4, 27 for the third row. And you're going to enter this into your calculator. If you need a reminder of how to do that, make sure you ask. Just check in with me or one of your classmates on how to enter that in. And when you enter this into your calculator and solve it, we should get x is equal to 45, y is equal to negative 10, and z is equal to negative 2. So you probably want to go ahead and pause the video so you can plug this into your calculator and check to make sure you get the same answers. And when you finish, you can continue. So moving on to row echelon form. So here are the three characteristics of a matrix in row echelon form. Any rows consisting entirely of zeros occur at the bottom of the matrix. So that's the first property. The second property is for each row that does not consist entirely of zeros, the first non-zero entry is a 1. We call that a leading 1. And then for two consecutive non-zero rows, the leading 1 in the higher row is farther to the left than the leading 1 in the lower row. And we'll look at some examples of things that are and are not in row echelon form. So now a matrix in row echelon form is in reduced row echelon form. So it has all three of these properties above, but every column that has a leading 1 has zeros in every position above and below its leading 1. So when we solve our systems using reduced row echelon form in the calculator, we end up with a matrix in reduced row echelon form. So example of a matrix in reduced row echelon form. So it might look like 1, 0, 0, negative 5, 0, 1, 0, negative 2, 0, 0, 1, 3. Okay, so a matrix in row echelon form, reduced row echelon form, every column that has a leading 1 has a 0 in every position above and below. So here's a 1, everything below is a 0. Here's a 1, a leading 1. Above and below are zeros. Here's a 1, everything above is a 0. Alright, so a little bit of vocabulary there for you. So let's take a look at some matrices and decide which ones are row echelon form, reduced row echelon form, or maybe neither. Alright, so in A, here's a leading 1 and everything below it is a 0. Here's a leading 1. The stuff below is a 0, but the stuff above is not a 0, so this is not reduced row. And then here's a 1. So we can see the first non-zero number in each row is a 1, and everything else is zeros. So this would be row echelon form. Alright, for part B, we notice that this row of zeros is not at the bottom, so it cannot be row echelon form, which means it can't be reduced row echelon form. So this is going to be neither. And if you want to pause and see if you can figure out these last three on your own, feel free. For part C, here's a leading 1. Here's a leading 1. Everything below this is a 0, but everything above is not a 0. Here's a 1, a leading 1, and then here's a leading 1. So this one would be row echelon form only. Alright, here's a 1, everything below is 0. Here's a 1, everything above and below is a 0. And there's all zeros in the bottom. Now, the only thing keeping this from being reduced row echelon form is this 2 here. Alright, so, but since I have leading 1s and my row of zeros is at the bottom, this would be row echelon form. And then over here, here's a leading 1 with zeros everywhere else. Here's a leading 1 with zeros everywhere else. The bottom row is all zeros. This would be reduced row echelon form. Alright, so the remainder of this Again, this is really just using reduced row echelon form, which we're going to do on the calculator, is solving a couple of systems. So if you want to write the augmented matrix and then go ahead and solve this, go ahead and do that. If you want to pause it, you can, and when you restart, the solution will be there. Otherwise, the solution is going to pop right up. So pause if you need to, and restart when you're ready. All right, so here's our augmented matrix. We're just pulling off the coefficients and what they're equal to. This should be a little bit different here. Not sure what happened there. So this should be a 7, -4, 18, and a 1, and it looks like I missed a column. All right, well, let's fix this augmented matrix here. It should be 0, 3, -2, 1, and then 7, -4, 18, and 1. There we go. And then the solutions here should be correct. We should have -4 for x, 1 for y, and 27 for z, and w should be 0. That's what that bottom row of zeros shows you. And finally, example 6 here, use reduced row echelon form feature on your calculator, which is basically the only way we're going to solve systems, to show that the system has an infinite number of solutions. So we'll take a look at our solution and talk about why it indicates that there's an infinite number of solutions. So we're going to do reduced row echelon form. So our matrix is going to be 1, 1, 5, -3, -1, -2, -8, and 5, -1, 0, -2, 1. And if you want to pause the video, and then you can write in the matrix that you get. So if you want to pause, and then when you restart, the matrix, the reduced row echelon form matrix that you get will be there, and we can talk about that. So pause now. All right, so this is the matrix that you should have calculated from the original system, and let's translate this a little bit. So what this tells us is that x plus 2z is equal to -1, and I'm going to go ahead and solve that for x, because essentially we want to solve for x, y, and z. So according to our solution, x would equal -2z minus 1. And then for the next one, we would have y plus 3z is equal to -2. And again, we'll solve this one for y. So we have -3z minus 2. And then this last one here, we end up with all zeros. So essentially, what this means is that z is equal to z. So if we end up with a row of zeros here, we have x is equal to an expression, y is equal to expression, z is going to be equal to itself. So what this indicates, an infinite number of solutions. Okay, we don't have one unique solution like most of the other problems that we've been working on. We have an infinite number of solutions. So if you get something like this, that's what the problem indicates. That's all I've got for you for this section. Make sure you get any of your questions answered, and we'll see you next time.